So now we'll continue with continuity, and now we'll get the whole formal definition. Like I said, the book started off jumping right into the definition and then using this breakdown right after, but I really think it was valuable to get the idea, to help get that established and to see how much we can do with the graphs. But now let's get that three-part definition. We're defining a function being continuous at a single x-coordinate at x equals a. And that happens if all three of these conditions are satisfied. So the first thing, well, we need to have a limit for that particular x-coordinate. If my function is going to be continuous at x equals a, it's going to be connected at x equals a, and the only way a graph to be connected is from the left and from the right, the graph has to be coming together at the same place. Now there's one little extra caveat here. The limit exists and is finite. We've already seen if the limit shoots off to any of the infinities, that can't be continuous. So that's what we mean here by being finite, that the limit is an actual number and is not an infinity. That's all we're saying. Okay, so by passing step one, now the graph is coming together. So just a quick little picture here. Maybe it's coming together like that. So this would be the x-coordinate a, and then by having that limit, whatever that y value is, that gives me the graphing property that the graph is coming together. Number two, f of a exists. Now no more left-right, you go directly to that a value, to whatever that x-coordinate is, and there is a point on the graph to go with it. And notice now I don't have to make that extra note about exists and is finite. We can't say f of 2 equals infinity. That doesn't make any sense. It makes sense to say the limit as x approaches 2 goes to infinity, but it doesn't make any sense to say f of 2 is infinity. That's nonsense. So that's why we don't have to make that statement here. And again, graphically, now I've got a point that goes directly with that a coordinate. But just because I have a limit and just because I have a point still doesn't mean the graph is connected, because I now need number 3. Wherever the graph is coming together, that has to equal the point value. So that would now just take this point and that would fill it in so that now this region is connected. So that's why those 3 steps, those 3 pieces are the definition of continuity. And if we go back and look at that first big graph, again, we had lots of discontinuities, but plenty of places where the graph was continuous. It was continuous everywhere over here. And any one of these spots, you've got a limit, you've got a point, and the limit and the point match. You've got a limit, you've got a point, and the limit and the point match, right? You've got a limit, you've got a point, the limit and the point match. But for the discontinuities, look at all the different problems. Here we had a discontinuity. Well, go through the 3-step process and we fail step 1. We do have a limit as x approaches -2, but the limit is positive infinity. Once you fail any one of these steps, doesn't matter if you pass 2 and fail the 3rd or fail the 1st, as soon as you fail any one of these qualifiers, you have a discontinuity. So, infinite limit, done. This is a discontinuity. Come to x approaches -1, and you don't even have a limit. From the left, we're up here at y is 1. From the right, we're down here at -2. Those don't equal. This limit does not exist. Once again, another discontinuity, and another one where we failed step 1. But now when I come over here to x is 1, I do have a limit. From the left, from the right, down, up, but I'm approaching the same spot. I'm approaching this open hole at -2, so I do get a limit. I do pass step 1. Step 2, oh, what happens at -1? I do have a function value. I get f of -1 equals -3, but these 2 values don't match. The limit was -2, the function value was -3. That failed step 3. At x equals 3, we had another discontinuity. We have a limit from the left, from the right. We're going to the open hole at y equals -1. So we do get a limit and it is finite. But then step 2, what is f of 3? There is no piece of graph to go with it. So this discontinuity fails step 2. And last, this discontinuity, we fail the limit. From the left, going to positive infinity. From the right, going to negative infinity. Therefore, no limit, and we fail step 1. Before I keep going, I want to make this very clear. We've spent a lot of time focusing on limits, and we were just asked limit questions. And now we haven't gotten that far, but now just seeing the definition, I hope you realize limits are now a necessary tool in order to answer some continuity questions. We are able to handle the continuity from the graph without limits, but now as we're getting the definition, we're going to see limits as a necessary part of continuity. So if you're still struggling with limits, you're going to struggle with continuity. That's why our first quiz is just going to contain limits, because you need that in order to be able to do this. And our last topic that'll come up before we get to our first test, limits are a part of that work. Okay, the second thing I want to point out here, before we move on and start getting to some equations, the second thing, look at the definition and let's see what happens at the spots where we had non-removable discontinuities versus where we had removable. Where did we go wrong here? And that can add a little bit to how we classify removable versus non-removable. Well, so let's see. Non-removable, non-removable, non-removable. And every single one of those failed on step 1. Limit was positive infinity, that's not finite. Limit did not exist, limit did not exist. Non-removable discontinuities. This whole idea of being able to change one point and fixing the discontinuity, that only works if you have a limit. Removable discontinuities pass step 1 and fail elsewhere. This one failed on step 3. The limit value did not equal the function value. This one failed on step 2, but they both pass step 1. So another way to rephrase this, a removable discontinuity is a discontinuity where the limit exists, and a non-removable discontinuity, either the limit does not exist or the limit is infinity or negative infinity. So again, just stretching. Do you want to write that out? You can. Plenty of people, it's kind of enough to just be able to see how to plug it in, but these removable, non-removable questions are still going to come up as we move into equations. So again, you may want to add that little bit to your notes. Removable discontinuities have a limit, and non-removable, either limit does not exist or the limit is some infinity. Okay, so we've got our definition, and now looking at the graph and thinking about everything we've already said with limits and seeing how limits are still a part of continuity, and thinking about still how we approach the first question, where is the function continuous? And we started off by answering that by finding where it is discontinuous. And what are the discontinuities? They're the weird trouble spots. The spots where you shoot off to infinity, the spots where the graph makes a jump, the spots where the graph has an open hole. We're looking for trouble. So, still haven't given you so much direction, but let's already jump into another problem. Let's find, for the following functions, we're going to use these directions for several problems going forward. So for the following functions, and just like I said with the graphs, I could always just ask you one piece. Focus on the discontinuities, focus on classifying them, or focus on where the function is continuous. But I'm going to do it all with these questions. So we see, no matter what the question is, we know how to handle it. So for the following functions, we're going to do 3 things. We are going to find and classify the discontinuities, and we are going to find where the function is continuous. Number one, we're going to start with a of x is x squared plus 2x plus 1. Still don't have any real information, and I tried not to pick too crazy or complicated a first function. Hopefully, just with a little bit of pre-calc or just a reminder, we know what type of function this is. By having the biggest power be x squared, we know this is a parabola, and if we do a little more work, we could eventually figure out that parabola looks like this. And by just now looking at that graph, thinking about the discontinuities, the trouble spots, the breaks, the holes, the jumps. Oh, by the way, I really should mention that as well. I only look at discontinuities and classifying as removable or non-removable. The book our book also talks about a jump discontinuity. That's what we're seeing right here, that the graph is jumping from this piece down to this piece. I don't care about that part, everybody. So don't have to worry about a jump discontinuity. We're just going to care about removable, non-removable. But thinking about the discontinuities, the breaks, the holes, the gaps, there are none. This has no discontinuities. And if it has no discontinuities, where is it continuous? It's continuous everywhere else. That means forever. It's continuous from minus infinity to positive infinity. Forever to the left to forever to the right, this is just one very nice connected parabola. It's connected no matter how far left or right you go. Now again, this graph does shoot up forever and shoot down, shoot up on both the left and right sides forever. So I can't keep drawing that. But if I did, I can keep going and keep going and keep going, and it's still always going to be connected. So I still kind of, I don't want to say I cheated, but I still kind of used graphing properties, so I had to understand the graph that goes with this equation to make these first points. Oh, and by the way, no discontinuity, so there's nothing to classify. If there are no points of discontinuity, we don't have to label any as removable or non-removable. And the second part, if you get the entire negative to positive infinity, that is all real numbers. Some people, they use, in a book, it's a bold-faced R. I can't make boldface on the board or on my note paper, so they put this extra line here. That R stands for all real numbers. And that certainly is the same as the interval negative to positive infinity. I prefer if you use the interval, since we're going to need it for a lot of other places, but this is just a nice reminder that, that notation, you'll see it in the book a little bit here and there, and just that expression, all real numbers, just to make sure we're making that connection. But back to the function, remember what we said with the graph. Look for trouble. Well, in an equation, what's trouble? We look for trouble with domain trouble. So that's things like we can't have negatives under a square root, we can't have zeros in a denominator, but this function doesn't have any of those problems. So that, without the graph, that could equally lead me to here. No discontinuities because this function has no trouble. Trouble, dividing by zero, piecewise functions, we're going to have to come back and discuss those a little bit. But in a regular type of function that's not piecewise, we're thinking about dividing by zero. So we don't have that issue here, no discontinuities, therefore continuous everywhere. The book takes this and makes a whole special theorem based off of this. As a broad category, this is what's known as a polynomial. So the book does make a nice little theorem. All polynomials are continuous everywhere. A polynomial will never have variables in the denominator, will never have to worry about dividing by zero, therefore will always end up with no discontinuities, and that we are continuous everywhere. For polynomial, just a reminder, that's again when your expression is only x's to positive whole number powers. So any radical can be rewritten as a fractional exponent. That is not a polynomial. If you have variables in the denominator or negative exponents, those are not polynomials. But this one is. Okay, so let's keep going. Number 2, let's look at b of x, and we'll look at 2x squared minus 10x all over x squared minus 25. Same question, everybody. Same directions. For this function, now b of x, let's find and classify the discontinuities, and then where is the function continuous? And this is where, if I only asked you about where the function is continuous, well, you gotta find the discontinuities first. You don't have to classify them, but that's the only real good way to solve this. I know some people might try and reach for their calculator, their graphing calculator, to try and do it in a manner similar to this, but that's where, are you zoomed in close enough? You know, little open holes in a graph, you don't see those on a graphing calculator. Okay, you'd probably spot an asymptote, but also your window. Most people have their graphing calculator from -10 to +10 on the x-axis, but not everybody. And sometimes we do. A lot of our x's, you notice, we kind of stay in that interval, but that doesn't mean we always will. We can have a discontinuity at x equals 12. That's certainly legitimate. So, like I said, this should be a spot that you can kind of confirm some work with a graphing calculator, but you shouldn't need it. You should be able to handle this by hand in a manner similar to what I'm going to show you. So I'm going to start off with the discontinuities, and those are going to come from where the denominator is 0. I prefer to factor this. I know some people can solve this one directly, but a lot of people forget the plus or minus when they take the square root. So by factoring, each one of these equal to 0. I get -5 from here and +5 from here. So 2 discontinuities. And now I am going to come back and finish the classifying. Like I said, I'm throwing the whole kitchen sink at you. I'm asking you all aspects of both continuity and discontinuity for all these problems. But if you were just being asked about continuity, we could finish. If it's discontinuous at these 2x values, it's continuous everywhere else. So before -5, up to not including -5, between -5 and 5, and then everywhere after +5. If you want to draw a little x-axis and just put your circles, right? You don't even need a scale. That's -5, that's +5. I am continuous for all the other regions. Those are the 3 intervals I have down here. So, continuity, I found the discontinuities, everywhere else continuous. Discontinuities, well, I've got them, but now how do I classify? Now I need the limit. That's where, okay, so far, no limit necessary to answer the continuity, but if I'm going to classify, I need the limit here. One at a time. I've got 2 discontinuities to check. I'll start off, what happens as x approaches -5. I'm a little short for room here, everybody, so I'm just going to write the b of x instead of the whole equation. But my first step, I'm plugging -5 in. So again, we need our limit rules. How do I start by taking a limit? I start by plugging in. -5 squared is 25, times 2 is 50, minus, oops, did I have some on here? Yeah, sorry. -10 times -5 is plus 50. In the bottom, 25 minus 25 is 0. This is a k over 0. This goes off to the infinities. I don't even have to keep going. If I really wanted to finish this limit problem, well, I'd have to approach -5 from the left, -5 from the right, figure out which infinity. But as soon as I get the k over 0, I know my limit is some infinity, And whether the limit is positive, negative infinity, or does not exist, either way, that tells me this is a non-removable discontinuity. -5 is a vertical asymptote. That's what happens. Again, whether you're shooting both to positive infinity, one to positive, one to negative, or both to negative, that's a k/0 when you're taking a limit. That's exactly what we're getting. Hopefully we're starting to make those connections so that way we don't have to keep going. I needed to start with the idea of a limit, but that was far enough that without finishing this limit, that still is enough information to confirm -5 is non-removable. But now, I have to test +5. Now when I do that, 25 times 2, I get 50. But now -10 times 5, I get -50. I'm getting a 0 over 25 minus 25. Now I'm getting 0 over 0. Well, that means, that tells me nothing. I got to go back, I got to keep going, and I got to start all over. And I have to manipulate. This one I'll manipulate by factoring. The top, just a little 2x as a GCF comes out. Bottom, don't think too hard about it, right? You already had to solve this equation. So by factoring here, that already got me closer to the factoring I needed here. Cancel my common factor. And now when I plug in, 2 times 5 is 10. Over 5 plus 5, I get 10 over 10, which equals 1. But even here, that's enough. That is a nice finite answer. I took the limit, I got an answer, the limit exists. Here the limit was either infinite or does not exist. You failed step 1. That is a non-removable discontinuity. Here you passed step 1, so that is removable. I don't have to keep going because realize, why did I know this was the key to finding the discontinuities? Well, in this type of function, that's exactly the situation where my function is not existing. So I'm kind of already taking advantage of the definition with that approach. By knowing what type of a problem exists in this type of function, a problem exists when the denominator is 0, and that is definitely a discontinuity. That is always going to be, you can't divide by 0 in a function, so those are always going to be places where the function does not exist. Okay, let's do that again. That's a mouthful. That was not the easiest problem, so let's see pretty much all of that again. Let's take a look at number 3. Still the same directions. We're still going to go do the whole kitchen sink. C of x. Let's look at the function. We'll do x squared minus 1 all over x cubed minus 10x squared minus 11x. Same situation. We are in the same situation we were with number 2. So I try to get you to understand the concepts, but there's no problem in also making some connections, but making the right connections from our experience. This problem, C of x and B of x, what do they have in common? These are rational functions. They're not polynomials, but they're polynomials over polynomials. Polynomial over a polynomial. So that is certainly something you could use and to realize, well, this type of function, this has a problem when the denominator equals 0. And again, that problem is directly leading to our discontinuities. Okay? So my discontinuities, well, when I solve this, x comes out, x squared minus 10x minus 11. Keep factoring. Nice trinomial, x minus 11 times x plus 1. All three of these equal to 0. Those three are my discontinuities. I have found all the discontinuities. And now I could change the order, but I want to focus on the continuous question next. If you wanted to start off, where is C continuous? Well, that's where you start. You find these discontinuities, but now I look everywhere else. And look how easy this is. People then say, okay, C of X is continuous, and they start listing their intervals, and they go negative infinity to 0, 0 to 11, 11 to -1, -1 to infinity. Do you realize what a little mistake that is? Right idea, but that's missing the point. You're throwing these values out, and when you solve these, you shouldn't always just assume that these x's are going to be in order. So just to make sure we're putting them in order, we have a hole at -1. We have a discontinuity at 0, and we have a discontinuity at 11. So these are the intervals. So it's not negative infinity to 0, it's negative infinity to -1. And then -1 to 0, 0 to 11, and then 11 to infinity. Those, I should say, are our regions of continuity on this function. And this is what I just said a moment ago. If you looked on your graphing calculator, you might notice the goofy spots on -1 and 0, but very few people would catch 11. It's not a very natural instinct to open up your window extra wide. And then even there, how wide do you have to open it? Do you have to open it up to 20? Do you have to open it up to 50? Practically speaking, like we just said, most of these problems, we kind of tend to stay between -10 and +10, but you never really know. So again, graphing calculator, a nice little way to check. Now that you have this information, now you could open your window past 11, but still, none of that is necessary. Just being able to do the algebra should be able to lead us to this answer. And now I'm back to the discontinuities, removable, non-removable. Again, some people take one example and take it too far. They see what we did here, and they go, okay, one will be removable, one will be not. Well, this only had 2 discontinuities. This one had 3. So should I assume one is removable and 2 are not? Or 2 are removable and 1 is not? You have no idea. You have to do every problem, treat it individually. It's possible all 3 are removable. It's possible all 3 are not. The only way we're going to know for sure is to go one at a time, taking the limit. So I'm just, going, no special order here, just going left to right. Here I needed to put them in order to make good intervals, but now I'm just testing one at a time. Testing x is 0. First thing I do is plug in. 0 minus 1, I get a -1. 0 minus 0 minus 0 over 0. K over 0, sum infinity. Don't even care what the rest of the answer. Is the limit infinity? Negative infinity does not exist. Don't care. I know 0 is non-removable. A infinite or limit that does not exist is non-removable discontinuity. Next, I'll let x approach 11. 11 squared is 121, minus 1 would be 120, the bottom. Now I'm going to do a little more work, right? Certainly wouldn't just expect you to know 11 cubed, so I'll pull out my calculator here. 11 cubed minus 10 times 11 squared minus 11 times 11. And I get 0. By the way, that really should not be a surprise. I wanted to show you that it was worth plugging in, but remember, where did this value come from? It already came from this work over here. So if we did this work correctly, we better get a 0 in the denominator. I mean, again, right from the get-go, something weird is happening at these spots. These were the values that made the denominator 0. So really plugging in, you could assume the denominator was 0, and now it's really just testing the top, and we're in the same boat. This is another k over 0, another infinity, so another non-removable discontinuity. How about -1? Minus 1 squared is 1, 1 minus 1. Okay, now we're getting a 0 over 0. And here's a bad habit, everybody. Some people see what I'm doing here, say, hey, he's not finishing. The problem didn't say find the limit. The problem said classify the discontinuity. Just getting this far in the limit problem tells me enough to know that these two are leading to non-removable discontinuities. But when you come to this one, 0 over 0, you can't assume good things will happen after. I can easily make an example that 0 over 0, you factor and clean up, and then you end up with a k over 0. So you have to make sure you go back and finish this problem. And now it is a 0 over 0, so I'm going to manipulate. So I'm going to factor the top, nice and quick. The bottom, again, I already did that work. Take advantage. Common factors that cancel. So I try and plug in again. I get negative 2 over negative 1 times negative 12. Now I could keep going. That's not that difficult, right? That's negative 2 over positive 12 equals negative 1/6. But that's enough. Whatever happens here, that is going to work out to a nice finite answer. And it doesn't matter what that finite answer is. 2 over 12, 1 over 6, or even a completely different, the square root of 2, 27, negative 112. You are getting a limit. The limit exists, so that makes this a removable discontinuity. Thinking ahead for a test, I need some work, everybody, okay? And this is enough just so I could see that you're testing a limit. And again, you know, we have to make the right connections. So let's make sure we're hearing those right things. So going back to the removable, non-removable, removable, it's all, and non-removable, it's all about step 1, the limit. The limit exists. Doesn't matter what the answer is, but if the limit exists, that's removable. The limit is infinite or doesn't exist, that's a non-removable. Okay, still have a few more to look at because we still have to talk about piecewise functions. And then very quickly at the end, there's a quick theorem that we should note before we move into the next section. It's not super important. Continuity is a major idea, but this last little theorem will be something we talk about quickly. But still first, piecewise functions. Same directions. Still thinking about where the function is continuous, finding the discontinuities, classifying removable, non-removable. So now we'll have function d of x, and we'll do this first one with a 3-piece piecewise function, x squared plus 1 when x is less than 1, 2x plus 1 when 1 is less than or equal to x is less than 3. Oops, I'm sorry, just 2x. That's all I want. I'm sorry, just 2x. And then the square root of x plus 1 when x is greater than or equal to 3. Now we're in a completely new category. We started with an equation that was a polynomial, and now we've got a theorem, or now we could just use the same result, no discontinuities because of no trouble, therefore continuous everywhere. Then 2 and 3, we saw rational functions, and we saw trouble comes from the denominator. And when the denominator equals 0, you have guaranteed trouble. But here in a piecewise function, think about going back in the limits, and when I talked about graphing piecewise function, where does weird stuff happen? Well, it doesn't have to happen, but there's a possibility that weird stuff happens where we change definition. Okay? That is a very, very interesting thing to consider. So now, this is not definite discontinuities, but I have possible discontinuities at our turning values. So in this case, we have 2 turning values, so we're going to have 2 spots to investigate. But here's a big problem, everybody. Some people just assume that those are discontinuities and then say D is continuous from negative infinity to 1, from 1 to 3, then 3 to infinity. But even if that was correct, if you don't give me work, I would always on a test have work must be included to justify, support your answer, and that's not enough. Again, these are only possible discontinuities. How am I going to know for sure? Are they discontinuities? I'm going to have to use the whole 3 steps. But I fail anywhere along the way, I know it's a discontinuity. I have to successfully complete all 3 steps to know it is continuous. So let's start with x equals 1. So I will take the limit as x approaches 1. And again, this is why we needed all those limits, piecewise functions. How do I handle this limit? Well, in this situation, I'm going to have to break it down and approach from both sides. 1 from the left, 0.7, 0.8, 0.9. Those are less than 1, so I'm going to use x squared plus 1. 1 from the right, 1.2, 1.1, 1.01. Those x's are in here, so I'm going to use the 2x. But now to evaluate, the left and the right have served their purpose, so I'm just plugging in plain old 1. 1 squared plus 1 is 2. 2 times 1 is 2. The limit equals 2. But that's still not enough. I can't just now say, okay, so D is continuous at 1. All we've done so far is pass step 1. Oh, I'm sorry about that. I was on the wrong. So here, limit of D. Here, 1 from the left. There's the piece I used. 1 from the right, piece I used, but I plugged 1 in both. That's how I got the answer 2. So I did get a limit. I passed step 1. But step 2, what happens when I go directly to D of 1? Well, that's okay here. Now, 1 has the equality here, so I will just plug that in here. Sometimes you get a whole extra piece. X is less than 1 here, x is greater than 1 here, x equals 1 is a whole separate piece. But here, x equals 1 takes me here, and I still get 2. Step 3, this, the limit, equals the function value. That this value we got from the limit is the same as we got from the function value. That is enough to conclude that x equals 1 is actually a point where the function D is continuous. It wasn't enough right here after I checked the limit. That was the harder part here, but I still had to do these other quick parts as well. Okay, and you don't need to label them 1, 2, and 3. I just wanted to do that just so you could match that up with the definition. But that's really the process. Start with the limit. If that works, then get to the function value. If that works, then make sure they match. If this didn't have the equality, then we wouldn't have a function value. We'd have D of 1 does not exist, and then we would end up with 1 as a discontinuity. But here, all 3 stages worked. 1 is a point of continuity for the function D. But now let's investigate x equals 3. Very similar. Starting off with the limit. And in this function, I'm going to have to, again, break it down. 3 from the left, 3 from the right, 2.7, 2.8, 2.9. Fall in here. Use the 2x piece. 3.3, 3.2, 3.1. Fall in here. Use the square root of x plus 1 piece. But when I plug in 3 here, I get 6. When I plug in 3 here, I get the square root of 4, which is 2. The limit from the left doesn't equal the limit from the right. So this limit does not exist. And now I don't have to keep going. As soon as I fail, whether I fail step 1, step 2, step 3, any point that you fail that you cannot complete that requirement for continuity, that leads to a discontinuity. So let's answer the first question. I'll squeeze it in up here. Where is D of x continuous? And I cannot tell you how common a mistake this is. People do this idea correct with their rational functions. It's discontinuous here, so it's continuous everywhere else. But for some reason, when people get to piecewise functions, and something like this comes up, people tell me D is continuous at 1. And that's it. But you have to remember, we already knew D was continuous a whole lot more than that. We knew these were the possible discontinuities. This is the only real discontinuity. So where is it actually continuous? Everywhere except here. Not just at 1, it's also continuous at 0, at -1, at 2, at 4, at 1.1, at 1.2. It is continuous from -infinity up to not including 3, and then 3 up to infinity. That is where D is continuous. This was not a discontinuity, this one was. But now, unlike here, we knew these were discontinuities, immediately led to the continuous part, but to figure out the classification, I had to do the limit work. But here, in order to know if these 2 points were continuous or discontinuous, the first thing I did was the limit work. Well, this is not a discontinuity, so don't worry about that. This one is. But you already have the work. The limit does not exist. Therefore, not only is it discontinuous, you also know that it is non-removable. Okay, everybody. One more piecewise, and then, like I said, one quick little extra aspect that uses continuity. So, one more piecewise function. What we have to, this is number 5. We'll call this one e of x. And let's let e of x be the piecewise x squared minus 6x minus 7 over x plus 1. So that ugly piece, but that is the definition when x does not equal -1. And then it equals 3x minus 5 when x does not equal -1. And this will be our definition when x does equal -1. So it's a little bit of a different setup for a piecewise. These pieces were based off of the intervals of x. These pieces are just simply based off of when x equals -1 versus when it doesn't. But we saw this with limits, and we need to be able to handle the continuity aspect as well. This one, there's only one turning point. So we only have one potential discontinuity. Let's focus on -1. I'll start by taking the limit. This one, left or right, approach -1 from the left, -1.2, -1.1, does not equal -1. Approach -1 from the right, -0.8, -0.9, does not equal -1. So I don't need the separate breakdown. I get to use this piece for both left and right. So I try and plug in. I get -1 plus 1, 0 on the bottom. All right, some trouble's coming up. But in the top, I get 1 plus 6 minus 7. I'm getting 0 over 0. So I need to manipulate. The top can be factored a little bit. X minus 7, x plus 1. These pieces can cancel. All the good habits I always said with limits, everybody, still maintaining those good habits. I don't mind you do a little cleanup here, but don't just write equals x minus 7 equals your answer. You still need your limit, because it's not x minus 7 equals -8. It's the limit of x minus 7 as x approaches -1. That equals -8. Okay? And that is right. Once I got to here, now I plugged in -1 minus 7, gave me the -8. So I passed step 1. I have a limit value. Well, step 2, what happens when I go directly to -1? Well, now I need this piece. So I'll get 3 times -1 minus 5. Hey, that also equals -8. And these two equal each other. So this actually was a potential trouble spot, but it actually ended up being a point of continuity, and that was my only potential trouble spot. So what is the question, everybody? If we were focusing on the discontinuities, the answer is there are none. There are no discontinuities for function e of x. If it's the continuous question, oh, and with no discontinuities, there's nothing to classify as removable or not removable. And then for where is the function continuous, well, there's nothing to throw out. So this, even though it was a piecewise function, you can't just say, we even saw it with the last one, I should have pointed out when we're done, you can't just assume these are discontinuities. They both might be, but they both might actually work out and be continuous. You gotta focus that those are the possible trouble spots and then go through the steps. Here, we only had one potential trouble spot, but it all worked out. So where is this continuous? Everywhere. Negative infinity to positive infinity. Okay, last idea, everybody. This is quite a lengthy section. A lot of aspects of continuity. That is definitely the main focus. The graphs, the equations, that's what you're responsible for on the test. And continuity, we don't see it as a super big idea, but we keep mentioning it as we keep going along. We're going to keep mentioning how so many properties as we move along initially rely on the fact that the initial graph was connected. So even if we don't keep seeing it over and over, it still lurks around calculus for the entire semester. That we like functions, that's most of the class, and we really prefer our functions to be continuous. That makes our lives easiest. Okay, so one little use is what we call the intermediate value theorem, or IVT for short. This comes up very quickly at the end of the book, at the end of section 1.8 in the book. And I believe I had like one, maybe two homework questions to go with this, just to test us a little bit to realize how theorems work. So what the intermediate value theorem says, first the statement. If my function f of x is continuous on an interval a to b, then for every y value, which is an element between f of a and f of b. I'm being a little informal in my notation. I'll draw a graph in just a second. This is not quite perfect. There exists a c value such that f of c equals y. A c value element, a of b. A very messy, ugly looking statement, but let's see what we're talking about here. So my function, first thing, the if. If, then. If statements in a theorem in math, these are the conditions that must be necessary in order to make the conclusion that comes after the then part. So if my function is continuous on an interval, it doesn't have to be continuous everywhere, but just for some interval a to b, we have continuity. And for a simple picture, let's do this. I don't care what happens outside of the interval a to b, but between a and b, my graph is fully connected, so my function is continuous. Then, here's the conclusion. Every y value between these two, this is why my notation is a little improper. An interval always goes from small to big. So it was definitely an assumption for me to say that the y value here would be smaller than the y value here. So that's why this is a little messy here, but it'll serve our purposes. It doesn't matter what y value you pick in between here. There is an x value in between here that will hit it. It has to. That's the idea of continuity. How do you get from here to here in a connected continuous fashion unless you hit all the y values in between? Now, I can go from here to here in different ways. I can go way above and then swing back down, but all these y values in between would still get hit. I could go up and down several times, but now all these y values would get hit several times. How would I not hit a y value in between here? I would need to have some sort of trouble, and that trouble would be something discontinuity. How can I draw and get from here to here and not hit the y values in between? Well, there's got to be some break or jump. That would be a way to go from here to here, but that has a discontinuity in the way. So again, this is really just trying to get you to think a little bit about how math theorems work. Again, try and get you to expand your understanding and experience with mathematics, particularly dealing with some of the language and the notation. And that's what this is trying to get us to do. So here's one very quick problem for us to see that'll force us to use intermediate value theorem. Let's prove f of x equal to x cubed plus x minus 1 has a zero, has a solution, an x-intercept between x equals 0 and x equals 1. This is definitely not obvious, but this is almost begging you to use the intermediate value theorem. So how would I use it? Well, so here's my proof. Step 1, I notice that my function is continuous from 0 to 1. F is actually a polynomial, so it's continuous everywhere. I only needed it to be continuous between 0 and 1, but I got even more than that. It's continuous everywhere. Okay, so I check that off. Well, now look at my conclusion. What happens with f of 0? Plug 0 in, 0 cubed plus 0 minus 1 is minus 1. What happens when I plug in 1? 1 cubed is 1, plus 1 is 2, minus 1 is 1. My function, let's look at the graph. I don't care what the graph really looks like, but at 0, I've got a value of negative 1, and at 1, I've got a value of positive 1, and my function is continuous, so I have to move from here to here in a continuous way. No matter how I do that, whether I do this, or I do this, or I do this, there is at least one place where I cross the x-axis, so that is my 0. And that seems weird, but we're done. We've completed the proof. Therefore, by intermediate value theorem, there exists a c value between 0 and 1 such that f of c equals 0. So it's a nice idea. I don't want you to go too crazy with this, everybody. It's a nice idea, but I think we've been very clear where you really need to keep your focus on 1.8. The definition of continuity and discontinuity, being able to classify your discontinuities, being able to work with both graphs and equations, and just like we saw with limits, discontinuities come at weird spots. A lot of our graphs are nice. They don't have weird jumps and breaks and holes like this. But for you to show me that you really understand continuity and discontinuity, you have to be able to handle those cases. So we're still looking at weird spots where we have to consider piecewise functions, where we have to look at places where the denominator could be 0. But again, a lot of good practice from the videos. Get into the homework, and let's have a good section.